Okay. All right, here we are. So anyway, so there's a whole bunch of gas laws. We're going to learn them from here on out. We're going to do the math of gases. And the first one we're going to learn is the relationship between volume and temperature. So the relationship between volume and temperature of the gas. When you heat up a sample of gas, when you increase its temperature, what happens to its volume? It increases. It expands, right? So we know this. This is how hot air balloons work. When we heat up the gas inside a hot air balloon, the gas expands and the volume decreases. So that's Charles' law. Charles' law relates the temperature and volume relationship. So we say they vary proportionally. That is, when we increase the temperature, we increase the volume. Increase temperature, increase volume. So we tend to show proportional relationships like this. V over T equals K. But for us, we find this to be more useful, that V1 over T1 equals V2 over T2. And there's a little picture of Jacques Charlet, Jack Charles. Jack Charles says, as temperature increases, volume also increases. Of course, he probably said it in French. Oui, oui. Le poisson. I told them I already got to it. It's very nice. Did you say you've already got to it? Yes, it's very nice. Okay, so this is a relationship where we have a volume and a temperature at one circumstance and a volume and a temperature at another circumstance. And this is how we're going to use Charles' law. We're going to say you have a sample of gas at this volume and this temperature. Then you're going to change the temperature or change the volume, and you'll measure the other thing. You're going to change the volume and measure the temperature, or you're going to change the temperature and measure the new volume. Critical to our discussions of gas laws is remembering that our temperatures must be in Kelvin. Our temperatures must be in Kelvin. And how do we turn a Celsius into a Kelvin? Add 273. Good. So we turn our Celsius into a Kelvin by doing C plus 273, and that gives us our K. Okay? Are you ready for some practice? Any questions before we do some practice? Then let's do some practice. If a balloon holding 4.8 liters of gas at 21 degrees is cooled to negative 18 degrees, what will be the new volume? I like to start my exercises by writing the formula down. So we're using Charles' law, so this is V1 over T1 equals V2 over T2. And then plugging the numbers where they are relevant. What is V1? V1 is 4.8 liters. What is T1? Aha! Yeah, we got to turn our 21 degrees into Kelvin. Good plan. Let's do that. 294. So 294 Kelvin. 294 Kelvin. Okay, I did something really important. Give me a thumbs up if you understand why I put 294 in the denominator. Okay, looks like most of you understand. Good. Temperature must be in Kelvin. And then it says, what will be the new volume? So we're solving for V2. And we're going to use T2. And what is going to be T2? Excellent. So negative 18 plus 273 will give us our Kelvin. 255? All right, 255. 255 Kelvin. And then we solve our V2. And this is where you just use your favorite algebraic technique. Some people are going to want to do cross multiplication. Some people are going to want to do divide and multiply by both sides. You pick. What I love about gas laws is there's always a big fat equal sign right in the middle. When you have an equal sign, what do you get to do? Check your work. Okay. So when you get an answer, always check your work. Cross multiply. cross multiplication is a good technique.
Does the unit?
Yeah, the units are going to be liters. Okay.
Liters? Oh, because you're finding. It's just never mind.
Out of black pens. Black pens. The only black pen I have is fairly faint. Look. I can try that. You first.
Mr. Byers?
Well, I thought that was like some sort of magic system where they can ink come
Well,
back.
I remember it from kindergarten, so I don't think it's really worth.
Fair enough. Not everything we learned in kindergarten works. Do we have a V2? 4.16. Can I round that up to 4.2? No. No, you can't. It's okay. Does 4.2 look like? Does that look like your answer?
Yeah.
All right. So we really should ask ourselves, does this number make sense? Well, the balloon decreased in temperature. It was cooled. So our volume should have decreased in temperature, which it did. Our temperature went from 294 to 255. It was cooled. And our volume went from 4.8 to 4.2. It was shrunken.
Check your work.
Check your work. Next. A hot air balloon holding 15,000 liters of gas at 12 degrees is heated to 85 degrees. What is the new volume?
Mr. Byers?
Yeah.
Is it going to be telling us what law we use when you give us like the problems?
For the worksheet? Yes. For the quiz? No.
So like, if it's out of the units it gives you, you figure out what law you're using?
Mm-hmm. You figure out what is given and what is not. So for instance, in all of these, pressure is not given. So you wouldn't use the pressure unit law. So yeah. In the worksheets you're getting next week for practice, you will actually be given what formula you're going to use. But on the quizzes and tests, you'll need to break yourself from that habit. Did I set this up correctly? Got all the numbers in the right place? Okay. Give me a thumbs up if you have your answer so far. Got an answer? That's like about 2/3 of you have an answer. And now more of you have an answer. What do you got for an answer? 18,400 something liters? 19,000. 19,000 liters. Okay. It's a lot of liters. So does it make sense? Does it make sense that heating the gas causes the gas to expand? Yeah, looks good. Okay, one more on Charles Law. Waiting. Yes. It's called significant digits. And we didn't have to learn it this year, but we really should get back in the habit of doing it. I'm going to get back in the habit of doing it because we're going to have to do it for chemistry AP and for chemistry dual credit next year.
So it's just whatever it teaches us, so you should have to.
Pretty much. Yeah, so it gives you 2, 2, and 2, so your answer will have 2. 2, 2, 2, so the answer should have 2. The rules are a little more complex than that, but that's really what it boils down to. Okay, if a 3-liter sample of air at 41 degrees Celsius is heated until it has a volume of 4.2 liters, to what temperature was it heated? Somebody have a temperature for me? 440? Yeah, usually. I mean, if you wanted to subtract 273 and got Celsius, that'd be fine.
Since they give you the thing in Celsius, you change your answer back to Celsius after you're done?
You have that option, but not necessarily. You don't have to, but you have that option. So unless it specifically says express in Celsius, you can leave it in Kelvin. If you did want to express it in Celsius, what would you do? Yeah, subtract 273?
Yeah.
What is that?
167.
167 degrees Celsius? Okay. Yeah. I mean, unless it specifically says express in Celsius, I wouldn't worry about it. So, how are you feeling about this Charles Law thing? Good? Okay. So the next law we're going to learn is Boyles Law. Bobby Boyle. Bobby Boyle. He investigated temperature or pressure and volume when temperature is constant. And what happens to a gas sample when you put it under pressure? If you increase the pressure of a gas sample, what happens to the gas? Yeah, it shrinks. So as we increase our pressure, our volume decreases. When you have something going up and something else going down, we call that an inverse relationship. So pressure and volume are inversely related. When one increases, the other decreases. When temperature is constant. So we can write inverse relationships as P times V equals K, or we can show them this way. P1 V1 equals P2 V2. V1 V1 equals P2 V2.
You're ready for practice now.
All right? We will be soon. Bob's Law. Bobby Boyle. know what the little C in front of a date means? You know what this means when you put a C in front of a date?
Circa?
Yeah, it means circa. It means around. Circa is a fancy way of saying around. So, like, when did that happen? Not around 1660. It was around there. No, just around. It was approximately that, around that time. Okay, practice. Are we ready for practice?
Yes, we are.
Okay. A bicycle tire has a volume of 8.2 liters at 4.3 atmospheres. What volume does it have when the pressure is increased to 6.1 atmospheres? So I like to write the formula down first that I'm going to be using, and then the pressure is going to be given to us at 4.3 atmospheres. And the volume is going to be 8.2 liters. And we want to know what the new volume is going to be at 6.1 atmospheres. So use your favorite algebra technique to solve for it. What's going to be the volume? Of B2, yes.
5.78.
5.78. Can I round that to 5.8?
Yeah.
So let's think about this for a second. 5.8 meters. We took the pressure and we increased the pressure, and the volume decreased. Is that in line with what we've learned? As pressure increases, does volume decrease? Yeah, it does. That's a liter. Liter with a half. There we go. Okay. Let's do another one. The helium balloon has a volume of 18 liters at 1.2 atmospheres. What pressure must it be under to expand to 23 liters? So we're going to cause the volume to increase, so we would expect the pressure to do what? Decrease. To what will the pressure decrease? 1? 0.95? 0.94? I'm giving to 0.95s and 0.94s.
It depends on how you're at.
Okay, so 0.95 atmospheres. So the volume went up, the pressure went down. Is that in line with what we learned? Excellent. Let's do one more. This is kind of an interesting one. If an empty flask with a volume of 480 milliliters at 1 atmosphere is corked and then half filled with water, what will be the pressure of air above the water? Assuming we don't shatter the flask. This is one of those read the exercise and figure out what it's asking.
Oh.
So what is the P1 in this exercise?
You must change it to liters.
1.0. 1.0 atmospheres. What is the V1 in this exercise? 480? So let's just go ahead and call that 0.480 liters.
Why?
Just because we want to use standard units whenever possible. And then it says, what will be the pressure of the air above the water? So we're looking for P2. What's going to be the V2? Yeah, it says it's half filled with water. So if the flask is half filled with water, then the remainder of the flask is going to be the air, right? So 0.240. All right. Okay. Yes.
Well, it's 2. But
It's 2?
Yeah, but how, it's 2 regardless of how you do it. I'm just curious, like, does that always happen like that, or why did we switch it? Just because
We switch it because next week we're going to learn a formula that has to be in standard units. So when you have the same unit on both sides of the equation, it doesn't matter if you leave it as milliliters or convert it to liters, but next week it will matter. All of our pressure units will need to be the same. All of our volume units will need to be the same. It'll need to be liters. So you said 2.0 atmosphere use. All right, cool. So now we got Charles' Law and Boyles' Law. There's another one we're ignoring called Gay-Lussac's Law. We're just going to skip it for now. But when you put Boyles' Law and Charles' Law together, you get the combined gas law.
Yep.
When you put P over P times V equals P times V, and V over T equals V over T, you get the combined law. Gay-Lussac's Law?
Yeah.
What do you think? What do you think is missing? What relationship is missing? Pressure and temperature.
What pressure?
Pressure and temperature.
What's
So
that? You didn't say yes.
I didn't hear you. So Boyles' Law is pressure and volume. Charles' Law is volume and temperature. Gay-Lussac's is pressure and temperature.
Is it just harder or something?
No, it's just rarely used. Anyway. So the combined law is simply the same thing as Charles' Law and Boyles' Law, but we just put them together. So we have pressure, volume, and temperature in one instance equals a constant equals the pressure, volume, temperature of another instance. We usually just skip the constant and say P1 V1 over T1 equals P2 V2 over T2. Okay? Ready to do some practice? Yay, practice. Here we go. Okay. So a sample of gas at 2.3 atmospheres, 3.2 liters, and 310 Kelvin. What pressure will it exert at 4.1 liters and 500 Kelvin? This one's going to be the math, and these are a little more complicated. Okay, check your work. Choose your favorite algebra technique to solve for your unknown variable. Some people are still going to do cross multiplication. Some people are going to multiply by both sides by something, divide both sides by something. I don't want to step on your math teacher's toes. If you need some help, I'll help you. Yeah.
There was no constant variable, so you just took that out.
Yeah, I just took it out. You don't have to. You don't have to. The equals K appears in textbooks and online, but honestly, you don't need it. You can just do P1 V1 over T1 equals P2 V2 over T2. anyone having some trouble with the math and needs a little help? Nope. Okay, what did you get for a pressure? 2.9? All right. And again, you got that fat equal sign right in the middle, so you can always check your work. Shall we do another? Why not? A sample of gas is at 1.8 atmospheres, 0.56 liters, and 290 Kelvin. What volume will it occupy at STP? What? STP? Standard temperature and pressure? You mean I have to memorize it? I am afraid so. So, B1 is going to be your 1.8 atmospheres. B1 is going to be your 0.56 liters. And your T1 is going to be 290 Kelvin. Nice. Now, STP stands for standard temperature and pressure. We talked about this yesterday. What is the standard pressure? 1 atmosphere. And what's standard temperature? Okay. So when you see STP, it's referring to 1 atmosphere, 273 Kelvin. Thumbs up when you have an answer you like. Okay, that's about half of you. 2/3. Okay. What do you got for a V2? 0.95 liters. Is that correct? 0.95 liters? Cool. Okay. So, how are you feeling with this whole combined law stuff? Last one. If the gas in a weather balloon is 1.0 atmospheres at 51 liters and 293 Kelvin, how cold must the gas get to contract to 30 liters at 0.75 atmospheres? people are losers. Some people serve food for a living. Some people get food served to them for a living. Just the way it works.
Some people aren't.
That's rich people.
Ooh, that's dark. So, temperature? T2? What is it?
129 Kelvin.
129 Kelvin? All right.
129 Kelvin.
129 Kelvin.
What?
You got 100 and what? Okay. And again, if you want to switch to Celsius, that's fine. You don't need to cover, that's fine. Okay, so that's pretty much all we have for today. The next unit we're going to do, or the next set of laws we're going to do, is called the ideal gas law. I think we're going to learn Graham's and Dalton's. But what we have today is just